Okay, so for this final problem, you have to impose both the mass conservation and the momentum equation. So we'll start with the mass conservation. And so first looking at the left-hand side, because we have a steady state, the mass inside of a control volume does not change. So this first term here, this is equal to 0 because we have a steady state. And now we have to look at the volumetric flow rate coming out of the control surface. And for that, we do have again to consider every single part of our control surface. So let's call this 1. The normal vector here is pointing to the bottom. 2. The normal vector is pointing here. 3. The normal vector is pointing normal to the stream function, to the streamline. And 4, with the normal vector pointing to the left. Now, because of our choice of control volume, this the volumetric flow rate out of 1 and out of 3 is equal to 0, because the velocity that we have is normal, is perpendicular to the normal to the surface. So here our velocity at the boundary, we have a no penetration boundary condition, so the velocity, well, is 0, but it would be well, it's actually 0, so it's easy. And on the top surface, our velocity is along the streamline, and therefore there is no component in the normal direction. So there is no volumetric flow rate out of 1, and out of 3 we only have to consider 4 and 2. So the volumetric flow rate out of 4, so we have a negative sign, times the double integral out of 4 rho u dot n ds. Here u is fully known, so the velocity vector u just has a component in the x direction. It's capital U, 0, and n is minus x. So this whole thing here, u dot n, will be minus u. So this is equal to integral from 0 to h naught of rho u ds. And then we have minus the integral along the outlet of rho u dot n ds, and likewise this here is going to be minus then the integral between 0 and hx, which is now the height here, if our top surface follow the streamline, of rho times u dot n. N is in the normal direction, is in the x direction, so u dot n just has the x component of the velocity field. There might be a small component in the y direction, but we are projecting on x anyway, so this is rho times u d, sorry, I shouldn't write ds, I should write dy. And this is equal to 0, and therefore for mass conservation we get that integral from 0 to h naught of rho capital U dy is equal to the integral from 0 to hx of rho u dy. Okay, so this is mass conservation, and now we impose the momentum equation. And here, again, for the momentum equation, because we have a steady state, the momentum inside of our control volume does not change. So this here is equal to 0 because we have a steady state. Now we are going to neglect the the body forces will neglect the effect of gravity. And so we are left with the flux of momentum through our control surface and the integral of the stress tensor, the stress vector, along our surface. Now remember, this stress vector for a Newtonian fluid is always minus, let me write it in full, is always equal to, this is from our discussion on the Cauchy stress tensor. It's always equal to the stress tensor times the normal vector to the surface, and our stress tensor is minus p times the identity plus 2 mu times the rate of strain tensor. So this dotted or times the normal vector. This is what the stress tensor is. And we always have to be careful about these two integrals. Those are always the two harder ones to compute. So let's start with the flux of momentum. Now, because there is no volumetric flow rate out of 3 and out of 1, we only have to consider the flux of momentum out of 2 and out of 4. But before we do this, when you write the momentum equations, you always have to remember you're not writing a scalar equation, you're writing a vector equation. That means that this equation here, you can write it in the x direction and you can write it in the y direction. Now, if you look at your control volume, it is clear that everything which has to do with momentum loss has to do, and even the drag force on the bottom surface has to do with the x direction. So you do yourself a favor if you directly just consider the x component rather than considering both. And because sometimes you can get confused with that. So it makes sense to right away project this equation onto x and only consider the x component of the momentum equation. Now I just saw that I'm missing a term here, which is the dot NDS. This here represents the volumetric flow rate, and so you are taking the volumetric flow rate of your momentum. Okay, so let's compute that. So let's compute this integral here. This is now straightforward since we've already done it for the mass, and we project this on x. So we only have the component, the flux through 4 and the flux through 2. Through 2, through this surface here, u dot n is negative capital U. So this u dot n is negative capital U. Right, this is here u dot n. And then we have the vector u, but this vector u we project on x, and u projected on x is capital U. So we have in the end rho capital U times ds. So this is really the integral from 0 to h naught of rho capital U squared dy. Now for 4, so remember always to be careful with the signs. 4, in terms of the volumetric flow rate, u dot n is just the x component of the velocity vector, because n is pointing in the positive direction. So u dot n is going to be equal to small u. This here is u dot n. And then we have to project on x. So we have u dot x, and u dot x is small u again. So we have times u. So rho u squared ds. And so finally, this whole thing becomes, so I forgot this minus sign. The minus sign from here goes here, plus integral from 0 to h of x, rho u squared ds. So this is the volumetric flow rate coming out, the volumetric flow rate of this is the flux of momentum coming out of my control volume, and here I've taken the flux coming out, and in the equations on the right hand side I have a minus sign here, so I have to be careful about that. I will have to be careful about this later on. And now let's take this term here, which is the sum or the resultant of all of the surface forces imposed onto my control volume. So it's the integral around the control surface of T n ds. Okay, and here we have to again look at really at all of the control, at all of our control surfaces. Now let's consider the inlet. At the inlet, you have to remember also that we are only looking at the component of the stress vector, which is in the x direction, because we only consider the x component, of the momentum equation. Therefore, we are not going to consider any tangential direction, and so what is acting in the normal direction? In the normal direction, if you look at your stress tensor, in the normal direction, it's the pressure which is going to act, right? So in the x direction here, what we have will be the pressure term, and we don't have viscous normal stress here because the flow is uniform in that direction. So on 4, the part which corresponds to 4 is just the integral from 0 to h naught of PA times dy. But actually, let me just simplify this whole discussion on the pressure. So let's consider our stress tensor, and let's first consider the pressure term. So because the pressure is actually uniform, right? So we only have P atmospheric everywhere. When we integrate the pressure, the part of the stress vector which is due to pressure along this close control surface, then we have 0. Right? So we have some pressure pushing in this direction. Remember, pressure always pushes in the normal direction. Here we have pressure pushing in this direction. Now, because h of x is a little bit bigger, it might seem that this is in imbalance, but this is not the case, because here we have also pressure pushing in the normal direction. Right? So it will mostly push downwards, but with a little component to the right, which will compensate the deficit of pressure which we have on surface 4 compared to surface 2. And on the bottom surface, of course, pressure is also pushing normal. So on the closed surface, if the pressure is uniform, then we don't have any contribution to the pressure. So I'm just going to not take into account here at all, and we'll only take the component which is due to viscosity. And here it is quite, you can observe that the only place where you have significant shear, and therefore you'll have significant gradients in the velocity, and where the only surface where you will have a significant component of viscous stresses is the bottom surface. Right? If you look at the top surface, once we reach the top surface, we have way past the boundary layer. The velocity field is pretty much uniform, and therefore the gradient of the velocity is equal to 0, and therefore the rate of strain tensor is almost equal to 0. So really the only surface we have to consider here is the bottom surface. So on the bottom surface, what we essentially integrate is so the only term we have here left is integral from 0 to x of 2 mu times the rate of strain tensor dot n, which is minus y dx. Now, we actually don't have to write the stress tensor, because this here is exactly equal to the force exerted by the wall onto a control volume, and so it's minus what we are looking for. So it's minus the drag. This whole thing here is minus d. Now, you may want to still write it down, and so if you want to write it down, then you just have to remember what the component of E of the rate of strain tensor are, and we're expressing the rate of strain tensor at the boundary. So at the boundary, V is equal to 0, but so the components are partial U over partial X. If we assume that V is equal to 0 everywhere, our rate of strain tensor will look like this: 1/2 of partial U over partial Y, 0, right? Which gives us the shear stress. Once we multiply by 2 mu on the y direction, so the normal is in the y direction, then we'll have the mu partial u over partial y, which we've discussed when we first discussed the constitutive laws. But let me just write that this is equal to minus d, and therefore if we put everything together, we're left with d is equal to, so I'm putting d on the left hand side now, so there is a plus sign, is equal to minus the volumetric, the flux of momentum coming outside of my control surface, so minus integral between 0 and h naught of rho u squared dy plus integral between 0 and hx of rho small u squared dy. And now getting rid of this minus sign, we get d equal to this, right? And here what we want is to have the same bound for the integral, right? We would want to have the same bound for the integral. That would make this whole expression easier, and we can do this by using the mass conservation. So if you remember from the mass conservation, we have this here. Let me just copy it. So if we introduce mass conservation here, right, we can express this integral as u times the integral between 0 and h naught of rho u dy minus integral between 0 and hx of rho u squared dy. And this here, from mass conservation, I should write it here, this here is equal to the integral between 0 and hx of rho u dy. So now I can rewrite d. My drag is equal to capital U times the integral between 0 and hx of rho small u dy minus the integral between 0 and hx of rho u squared dy. And now I can put everything under the same integral. So this is integral between 0 and hx of rho u squared times small u divided by capital U times 1 minus small u divided by capital U dy. And I do this to have here the momentum thickness appear. And so to do that, let me just take this rho u squared out of my integral. I have rho u squared integral from 0 to hx small u capital U 1 minus small u capital U dy. And we did this actually for any arbitrary h of x. So in particular, we can just now bring h of x to infinity, and this equality will still hold. So I can just write that this is equal to rho u squared 0 times the integral from 0 to infinity, small u divided by capital U, 1 minus small u divided by capital U dy, and this here is the momentum thickness at x. Also note that when you apply the momentum equation, you have to be very careful with your signs. And in that case, you expect that the drag onto the plate is positive, and indeed you do get a positive number. Rho u squared is positive, u is positive, and small u divided by capital U is less than 1, therefore this number is also positive. And so we do have a positive drag. Always do those little checks at the end.